Good afternoon. Brilliant. Today's lecture is a story about a journey. And it's about the journey that the Earth makes and also the journey that we have made to understand about how the Earth moves. Because it may not be apparent to us on an everyday basis, of course, but you have to remember that the Earth is in constant motion. Not only is it rotating around its axis, it's revolving around the sun, and then the sun is on its own journey through and across the Milky Way. And today we're going to talk about how we pieced all of that together to get our modern picture of the heavens, and then what the next steps are. What are the next things we need to know about how the Earth moves? Now, to begin with, there are some very simple observations that anybody can do with the unaided eye, which are all clues, and you just need to watch the sky for long enough. Or alternatively, you don't watch it very long and you cheat and you have a time machine.
What if I went faster?
So as I say, that's cheating, but it does illustrate some of the simple things we all know about. That day turns into night, turns into day in an endless cycle. Not just that, but you have the sun and the moon make a steady progression across the sky every day. And the moon changes its shape, it changes its phase, in other words, the amount of the sunlit side we can see, and it moves at a steady rate against the backdrop of the stars. And in terms of those stars, they may be fixed into certain positions relative to each other, but which of those patterns we see depends on the time of night, because those patterns move across the sky continually. And then from one night to the next, a fixed pattern of stars will rise 4 minutes earlier than it did the previous night. And if you wait a year, then you get to the same pattern repeats itself at this rising exactly the same time. And there are all these observations that you can make, and they inform you already a lot about how the Earth moves in the sky, but it's not obviously apparent from those, immediate facts. The ancient civilizations mapped out this behavior and used it, all the astronomical observations, to construct calendars. And we know this from archaeoastronomy, when you look at certain structures, ancient structures, whether it's looking at something like Stonehenge, where the relative alignments of stones tell you something about midsummer or the solstices, or it's the Kurikul Tower in Chichen Itza in Southern America, where there are certain windows that let in the light from the sun or Venus at their sort of northernmost or southernmost extremities in their movement around the sky. And these are important because this regular repetition of the sun and the moon and the stars were important not only for navigation, but for also marking the passage of time. They're important for agriculture, knowing exactly when was the good time of year to both sow your harvest and then, sow the seed rather, and then reap the harvest. And one way to recognise bits of the sky and recognise when certain features were rising and getting the passage of time through the year was to group these stars into fixed patterns, the things that we know today as constellations, of course. You may recognise some of them in this image. And these would often be to create creatures or characters from mythical legends, often with a very healthy dose of imagination, get a group of stars into some of the more strange constellations. And a lot of the constellations we use today were handed down from the ancient Greeks. For example, here we have an atlas from 1603 showing the constellation of the Great Bear. Actually, it was quite a friendly bear. And the very famous one of Orion. And we don't just have the Greek constellations, there are constellations handed down from other cultures. But in the West, and certainly in modern astronomy, we use the ones that derive from probably Hipparchus. So Hipparchus was around in the 2nd century BC, and he actually made catalogues of the stars. He probably catalogued about the positions of 850 stars, grouped them into about 100 constellations, and marked the position of these stars within probably about the size of a couple of full moons in the sky. That's quite accurate for observations just with the unaided eye. He's also the guy that was responsible for our very useless system of magnitudes, measuring brightnesses of stars. So we don't have a copy of his catalogue. However, here's a replica of a statue from the 2nd century AD, and you can see his atlas, and he's carrying the heavens on his shoulder. And you can see the tropics of Cancer and Capricorn, you can see the equator marked in it, and several of the constellations are thought to represent Hipparchus's original star atlas and his mapping of the stars. Of course, they weren't just Hipparchus's constellations. The Chinese were avid astronomers. They believed a lot in the omens, and they recorded a lot of the observations of things that changed and how they changed in the heavens. They created their own star maps. Again, different groupings of stars, though in practice there's one that is quite recognisable here. It's about the only constellation we have in common through several cultures of this idea of a character, of a hunter or a warrior. In the Chinese, it's Shen. In the Greek, it's Orion, the hunter. And you find that it's a very characteristic constellation in the winter skies. Of course, today, we've reduced this all. All the constellations been refined and reduced to about 88. And it's not just the pattern of stars in the constellation now. Each constellation is assigned a patch of sky. Here's the boundary around Orion. And we have now mapped the sky so that every star in the sky belongs to one of those 88 constellations. And, it gives I'll talk about some of the reference points we use for those stars in the sky. But if you imagine seeing the stars without any of the knowledge we have today, they are all at immense distances away. We know now, of course, that constellations are just line-of-sight groupings. Some of these stars are further than the others. So with Orion, for example, if we want to do a full 3D, sorry, that should be moving. Oh, it was moving. Sorry, I'll get the technology to work with me in a minute. Here we are. So it looks like a 2D pattern on the sky. But if we're able to shift round Orion and move round to the side, you will see that the stars that make up Orion are at very different distances. So, for example, Bellatrix in the shoulder is only about 240 light years away from us, compared to Betelgeuse, which is at 640, Rigel's at about 800, and Alunam in the belt is a full 1,300 light years away. So they're not real groupings of stars, they're all at different depths of us. So you have to remember, we know now that the sky is three-dimensional. That was not obvious originally, and indeed you have this idea of a celestial sphere, where in all the ancient cultures, the stars were perceived as being on the inside of a giant shell that was concentric with the Earth. And so very distant points of light embedded in the celestial sphere. And because we see the celestial sphere and the pattern of the stars rotate around the Earth during the night, it's obvious that the Earth stays still and the celestial sphere moves around us. And you'll find that is the basic model from a lot of the ancient cultures. Certainly the ancient Greeks knew the Earth was round. They could see the moon was round. They could detect the sun was round. It's not a great leap of faith to infer that the Earth is round. You can also see the shape of its shadow during a lunar eclipse here that the Earth casts around shadow. And of course the Greeks were very much into perfect shapes such as circles and spheres. And so it's only natural when you think about how bodies move through the solar system, or what we now know is the solar system, where bodies move through the sky, that they move on those perfect circles. And the most natural interpretation is to put a motionless Earth at the centre of all the heavens. Now this fixed shell of stars that we see right out here at the edge of the heavens, that rotates around the Earth. And then we see the moon and we see the sun rotate around every day, and they move around the Earth. And so you have the Earth at the centre and everything else moving on those perfect circles. Everything lying in a flat plane apart from the celestial sphere. And I'll talk about how we know that in a minute, but moving in these flat circles. But there are difficulties about explaining everything that you could see in the night sky just with this simple model. And the problem is that you can explain the sun, the moon and the stars, but the planets are another matter. Now, planets, that planet means is the Greek for wandering star, behaved in a less predictable and a slightly more subtle fashion. Now, we know the sun and the moon move relative in one direction at a constant speed relative to the stars. Planets don't do that. First of all, they vary in brightness over periods of weeks to months. And when they're at their brightest, they sometimes do a very strange motion across the sky. Here's just a time-lapse showing Saturn going through what's known as retrograde motion. So prograde is when it moves in the traditional way across the sky from west towards the east. But with the planets such as Mars and Saturn and Jupiter, every so often they will move across the sky and then reverse direction. In fact, here's just a time-lapse over a few months of Mars relative to the stars. This is your normal progression, but then it'll suddenly loop back and go the wrong way across the sky before reverting its original direction. And this was a problem to explain with just those circles of orbits going around the Earth. And so the ancient Greeks had to kind of refine their model. And the introduction of something called an epicycle to try and get this retrograde motion of the other bodies moving around the Earth. And if you imagine the Earth at the centre, this may be the orbit of the planet, but the planet doesn't actually follow that circle. Instead, it travels around on an epicycle that follows the big cycle, which the Greeks called the deferent. And if you like, it's a cosmic spirograph. And there are moments where the planet appears to loop back on itself. And so from the vantage point of the Earth, that creates this retrograde motion of the planet in the sky. And so the original simplicity of the model that we derive from Ptolemy starts to get quite complicated, because not just are the planets going around the Earth, but they're going around on the epicycles on the deferent that travels round the Earth. And then further refinements to take into account the fact that planets don't move at a constant speed meant that actually the Earth had to be slightly displaced from the centre of the deferent. And so you introduce things called the eccentric, which is the amount the Earth is shifted away from the centre. And the deferent still goes around the Earth, but now it's centred on something called the equant. And you begin to see it starts to get a little bit convoluted. Nonetheless, by the end, this is the sort of Ptolemaic model. This is your classic geocentric, Earth-centred universe. The Earth at the centre, everything else travelling round, the sun further out from the Earth, of course, and everything, all the planets travelling on those epicycles on the deferents. And this, in fact, proved to be a very good model. It could predict the motions of the planets very accurately, including that retrograde motion. It was a very successful model, and indeed it did for many centuries after it was derived. Now, after the Greeks, there wasn't a huge amount of astronomy done, certainly in Europe. Most of the astronomical, while Europe was going through the Dark Ages, a lot of the astronomical tradition was being carried on in Asia, in China and India, and also in the Arabic countries, the Islamic scholars. And it was still a case of doing precise measurements, recording observations, cataloguing the stars, building atlases. And a lot of our star names, for example, come from the Arabic name from stars, because those are the ones that are being handed down to from those medieval scholars. And it wasn't, though, until we hit the European Renaissance, the scientific Renaissance, that the actual fundamental view of an Earth-centred universe had to change. And the person responsible was the Polish mathematician Nicholas Copernicus. And it's thought that perhaps his interest in revisiting this idea, the model of the heavens, was reawakened by and certainly other scholars at the time, a rediscovery of Ptolemy's original publication, the Almagest, where he set forth this Earth-centred universe. And Copernicus was the one that actually challenged this view and turned our view of the heavens on its head by putting not the Earth at the centre, but the sun at the centre. And he used logic to try and argue the relative position and distribution of the planets. again, by using observations that we can all make. Now, sometimes you can see several planets in the sky at once. Here you have, or it may not be obvious, certainly from the back, but I'll just tell you, you've got the position of Mercury and then Venus, and up here we've got Mars and Jupiter. I'll talk about them in a minute. But the thing about Mercury and Venus is that they are always close to the Sun. You only ever see them in the twilight sky at sunset or before sunrise. And in fact, Mercury is never more than 28 degrees away from the position of the Sun, Venus not more than 47 degrees away from the Sun. And so Copernicus used those arguments to say, okay, they're closer to the Sun because they orbit around the Sun, closer to the Sun than the Earth does. And you interpret these observations of how Mercury and Venus behave as, here's a time-lapse picture taken over about a fortnight. This is how Venus changes position. Here, you can just see, is the loop that Mercury makes from one night to the next in the sky. And so Mercury will move away. So the Sun's down here below the horizon. Mercury moves away over the night. So it reaches what's called its maximum elongation towards the west, and then it sinks slowly back towards the Sun again. And then we know it moves behind the Sun from our point of view, and then we begin to see it at sunrise, where it again moves out to its maximum elongation and then goes back. And so we're seeing the orbit of Mercury round the Sun. And therefore, his predictions were, first of all, that both Mercury and Venus should move at some points between us and the Sun. This is a transit. We should be able to see the silhouette of the planets against the Sun. This had not been observed at the time. In fact, it wasn't verified until much later, till 1639, when the first transit of Venus was observed, where the silhouette of Venus moved across the surface of the Sun's disk. The other prediction that he makes is that Venus should show phases. And this is not what you see in the Ptolemaic model, the Earth-centered model. Here, when Venus has got its full face towards the Sun, we're not going to see it. We're not going to see all the phases of Venus. If Venus is going around the Sun, it should show phases. And again, this was not something anybody could see. So he made two predictions, but they could not be verified experimentally. Now, the other thing that he looked at were the fact that with Mars and Jupiter and Saturn, they were not always confined to being close to the Sun. You could sometimes see them in the middle of the night, which meant they're the opposite side of the sky to the Sun, which means the Earth should lie between the Sun and these superior planets, and therefore their orbit should lie out beyond the Earth's. And by using all this logic, he built up the heliocentric universe that puts the Sun at the centre and correctly puts Mercury, Venus, Earth with the Moon going round, Mars, Jupiter, Saturn, and then still the celestial sphere orbiting around. Now, of course, this was against the doctrine of the Catholic Church at the time, so he did postpone publication until the year of his death. And again, he was still refining the models, because even though he got this beautiful model, which we now know to be essentially correct, it still did not produce better predictions than the Earth-centered model from Ptolemy. And he still had to tinker with it because Copernicus still put everything on perfect circular orbits. And he had to introduce epicycles to account for some of the variations in brightness and speed of the planets and their orbits around the Sun. So there were some things that still didn't fit. It may look a more elegant model, but it was not necessarily more accurate at making predictions. So there were people who were trying to prove this model false or right. And the key person is Tycho Brahe. Okay, which I'll come back to in a minute. I just wanted to say the one thing that Copernicus's model does right is accounts for retrograde motion. Planets closer to the Sun and the smaller orbits are travelling faster than those further out. And so if Mars is further out from the Sun than the Earth will lap Mars occasionally, and also true for Jupiter and Saturn. And so if you think of our viewpoints as we kind of run past Mars travels this far in the time that we travel this far. In terms of our perception of observing Mars against the background sky, it's going to make this apparent loop. And so retrograde motion for the first time could be accounted for very beautifully in this model. However, this idea of things being displaced against the background, again, compared to our viewing angle put a big problem in terms of Copernicus's model. And this was realised by Copernicus, but it was also challenged very much by Tycho Brahe, he wasn't particularly in favour of this heliocentric model. Now, Tycho Brahe was a Danish astronomer who made state-of-the-art astronomical instruments. The telescope was not yet invented, was not yet being used for astronomical observations. But Brahe was inspired by the appearance of what we now know to be a supernova, but a new star in the heavens. This came about sort of 1572, so about 30 years, we're talking 30 years after Copernicus' death, where a bright new star appeared in the constellation of Cassiopeia. There's the W, here's the new star. It was there for about 18 months, and it challenged this notion of the heavens as being perfect and unchanging. And Tycho tried to measure how far away that star was, and he showed that it was part of the celestial sphere. It was the same distance as the other stars, and therefore it was part of, maybe the heavens weren't unchanging. He did the same feat several years later when there was a spectacular, one of these great comets in the sky. He showed its distance was at least 6 times further than the moon. Therefore, it was not something that occurred within Earth's atmosphere, but something that belonged to the realm of the planets. And for both of these observations, he used parallax, an observation of how something appears displaced against the background of stars depending on where you observe it from. And his contention was that this should also be true if the Earth was moving around the sun. So just to step back to the comet and to the supernova. Imagine you're observing something from 2 different positions on Earth, and you're seeing how that object compares against the background stars. And how much is shifted compared to the background stars depends obviously how much you're separated on the Earth, but how close that object is to you. So if you're something in your atmosphere, you should observe a big displacement relative to the backdrop of stars. If it's somewhere about the moon's orbit, and obviously not to scale, okay, but you would see a much lesser shift. And then if it's out beyond in the realms of the stars, you should see virtually no shift at all. So in terms of the comet, it showed less of a shift against the background from 2 different sites than the moon did. Therefore, it was further away than the moon. And so remember, the amount of parallax you see depends on how far something is away. But it also depends on your motion or how far apart your viewing angles are. The catch is, if the Earth is moving around the sun, you have 2 great places where you can observe things that are very widely separated. Instead of the baseline of how big the Earth is, you use one side of the orbit to the other around the sun. So, for example, if this is the Earth's orbit around the sun, here you are in July, here you are in January, and you're observing one star or object, you should see it, well, just make it clear we're observing this one, shifted relative to those background stars because of your much greater viewing position. So from here, you line it up to, it appears around, say, that star. 6 months later, you see it lined up around that star. And this is an annual pattern that should be seen in the stars called parallax. And if Copernicus was right and the Earth was moving around the sun, Tycho said you should be able to observe that parallax. Now, Copernicus knew about this. He had already used the fact that you didn't see parallax to say, well, the stars are actually much further away than we thought. That's why you don't see parallax. Tycho wasn't convinced, and he made astronomical observations over many years. He did not see any stellar parallax, any of this constant shifting. We know now, of course, that he wouldn't have done because he was only using the unaided eye, and with very precise instruments, that's still not enough to detect the amount of annual stellar displacement. So he wasn't convinced. However, all his data set went to his assistant, Johannes Kepler, who inherited them and was much more in favour of the heliocentric model. And he had a much more vested interest in using Tycho's observations to try and challenge and prove Copernicus's model. And he did this in a number of ways. He kept tinkering with the model, trying to get it to fit the data. And his inspiration was to relax this notion of perfect circular orbits. He said instead that the planets move around the sun in elliptical shapes, so squash circles, and they just need to be slight deviations from that perfect circle. And you have the sun at one focus of the ellipse, such as here. And from that, you don't need the epicycles. You can have the heliocentric model, all the observations fit if if the planets move around the sun in ellipses. And from this he got various laws of planetary motion, such as the fact that if you join a line between the planet and the sun, it sweeps out equal areas and equal times. This means that the planet moves faster when it's closer to the sun. It moves more slowly when it's further away from the sun. He also derived laws of planetary motion that related the time that a planet took to go once around its orbit to its distance from the sun. And somehow then it was a much more elegant, a much simpler model than the Ptolemaic system, and it seemed much more viable. However, there was still no actual proof, and the proof had to wait till the first new data, the first real new game-changing data for centuries, and that came with your astronomical telescope. And of course Galileo, who did, revolutionize so many areas of astronomy. But for example, in terms of understanding how the Earth moves, he was able to show, first of all, that Venus showed the phases that you'd expect. Here's the moon, here is Venus. Venus in his notebook, and you can see the relative size of Venus through the telescope corresponds with the phase that it's showing, exactly as you'd expect for something that you're seeing as it orbits round the sun from a viewpoint on Earth. And not just that, his observations of the moons of Jupiter and how they moved around the giant planet. First of all the motions of those moons exactly behaved according to Kepler's laws of planetary motion, so it vindicated what Kepler was saying. But not just that, the fundamental thing this was showing is there could be other centres of motion within the heavens other than the Earth, and therefore the Earth did not need to be the centre of the motion of the moons around Jupiter, and therefore it didn't need to be the centre of motion for the whole of the heavens. So of course his observations were clearly in favour of the heliocentric model. And he published a pamphlet about this, the Sidereus Nuncius, the Starry Messenger. And this was meant very much as a public education. It was written much more colloquial Latin. It didn't include the data and the equations and formula characterised as scientific publications of the day. It was a sort of pamphlet meant for an educated public. But again, this got him into trouble with the doctrines of the church at the time and the belief that there was an Earth-centred universe, and he had to retract his observations. He had to recant the idea of the heliocentric universe. He did revisit it again later. Much later in his life, he approached the argument from the point of view of a three-character drama where different protagonists argue different points. But again, that got him into trouble because it was too heavy a promotion of the sun-centred universe, and he was again forced to recant both this drama and his belief that the Earth in fact moved, and was forced under house arrest for the rest of his life. Nonetheless, he was right. The observations and continual amassing of observations, now telescopes were in order, began more and more to support this view of the universe, and it became more in favour. And this showed us how things move, but it wasn't, of course, till Newton came along with his laws of gravitation that we began to understand exactly why things move. And there are consequences in that you no longer need the exact celestial heavens to move around the Earth. Instead, the Earth rotates. Now, this is a Foucault pendulum, which is just demonstrating the rotation of the Earth. It's a very long pendulum. It's free to swing in any plane. And the key thing is that it swings absolutely and the Earth rotates underneath it. And so over a course of a day, it'll move relative to the Earth. And it depends where you are on the latitude of the Earth. But this is one way of demonstrating the fact that the Earth rotates. And of course, it's the rotation of the Earth that makes the stars move throughout the night. So the stars now are seen as a fixed celestial sphere, and the Earth is rotating underneath them. So the rotation of the Earth is tilted, and we'll talk about to what, because a lot of this story is also going to be about frames of reference. How do you know something's moving? What do you measure it in comparison to? Now, we still talk about the celestial sphere. We know, of course, as I said, that it's a three-dimensional construct, but it's still useful for positional astronomy to think of it as a shell at an infinite distance away with the fixed pattern of stars on. And we can have relative positions on it which are absolute, because the problem is the Earth is turning the whole time. And if you want to relate the stars to the Earth, you have to fix some positions that don't move relative to the Earth. And one way to do this is if you extend If the Earth is rotating in this direction, you extend the direction of this axis of rotation out to where it meets the celestial sphere. You have the north celestial pole, and you have also, if you extend out the equator, the celestial equator. So this is just extending it out to the sky, and you have an imaginary path across the sky, which is the celestial equator. And the Earth is moving relative to these absolute fixed points. But of course, when you look from Earth, the stars all seem to orbit around the poles. We call this circumpolar rotation. Now, here's a time-lapse picture. So you're looking towards the North Pole here, and this can only be about half an hour, and you can see the stars trailing out their motion. But you get the idea that it's all concentric due to the Earth spinning on its axis. So if you look towards the North Pole, you were seeing everything moving around that pole. Nearer to the pole, they're moving almost sort of flat to the horizon. If you move to the equator, of course, if you're at the North Pole, everything's circumpolar because you're right spinning underneath that pole. If you move to the equator, you are moved round 90 degrees to an observer at the North Pole, and therefore the stars and the planets all seem to rise vertically up in the sky. So this is over Kilimanjaro. And then, of course, if you're at different places in between, the stars will rise and planets will rise at an angle to you. So all this motion in the sky is due to the Earth's rotation. Now, there's also, I talked about us being tilted, and the comparison as what are we tilted to? We're tilted 23.5 degrees to a vertical axis. And that vertical axis is defined by the plane that the sun and all the planets lie in. Because if we go and look at the track of the sun and the moon and all the planets, they all follow the same broad band across the sky. That means that, like marbles rolling around on a table, they're all orbiting round in a flat plane. And that's tilted from us. Again, its appearance depends on your latitude. And not just that, but how we view them against the stellar background depends on where this path is in the sky. So to explain, you've got 360 degrees in a circle, and the Earth takes 365.25 days to go once round its orbit. That means that relative to the backdrop of the stars, the sun has to shift by about 1 degree a day. That's the 4-minute shift that you see in the star patterns, which star patterns come up when the sun sets. And it's because the relative angle that we see the sun against the background stars. And the projection of the sun against the stars, those constellations are the ones that make up the zodiac. And they lie in what's known as the ecliptic, which is just the plane that all the planets and the sun and the moon appear to orbit the Earth around, but the path that they take across the sky. So relative to that, if these are the directions according to the Earth's rotation, this is the frame of reference, which is the rest of the solar system. We are tilted by 23.5 degrees there, which means that this ecliptic is tilted compared to our axis again by 23.5 degrees. And the point where our celestial equator meets the ecliptic, there are 2 points. They're called the equinoxes, and here's the vernal equinox. And the problem is, if I want to tell you where a star is in the sky, now I can do it in 2 ways. I can say, well, it's yay far around the horizon and it's yay far up from the horizon, which is great for that moment. But you might be observing from a different latitude, and so your horizon will be different from mine. You might be observing at a different time of day, and the Earth will have rotated, or different time of night even, and the Earth will have rotated. And so relative to the horizon, your star will be in a different position. So we need a way of measuring or referring to where stars are that is independent of the Earth's motion. And this is where we use the frame of reference of the whole of the solar system, and again, how that's projected onto the sky. So we use a system that's like latitude and longitude on the Earth, but is anchored to the celestial sphere and is not dependent on the Earth's motion. So in particular, we measure how far around the celestial equator, because remember the equator of the Earth and how it's projected to the sky is unchanged as we're turning round. So from this vernal equinox, we measure around the sky, that's right ascension. And then from the projection of the equator in the sky, we measure either north or south. So that's the equivalent of latitude, and that we call declination. That's measured in degrees. And so right across the sky, we have an imaginary grid across the celestial sphere. Again, measuring from there how far round we go and how far up and down from the celestial equator. And that gives us our coordinates that are independent of the Earth's motion. Of course, it's not quite that simple. It never is. If only the Earth were that well behaved. There are other motions which continue all the time. The Earth doesn't just rotate and go around the sun. There are then substantial changes towards that. The first thing, of course, is that because the Earth is spinning, the centrifugal motion has made the centre of the Earth slightly wider than it is at the poles by about 40 kilometres. It's got what's known as an equatorial bulge, like we all do in middle age. It's kind of slightly tubby around the middle. And the net effect of the gravitational pull of the sun and the moon on that equatorial bulge, well, they want to pull the Earth round so that it's sort of perpendicular to the rest of the solar system. Unfortunately, because the Earth is spinning, this just has an effect of pulling the axis of rotation round, like is happening in this gyroscope here. And so we have something called precession, which is that the axial tilt remains the same, 23.5 degrees, but it gets pulled round to kind of sweep out a conical shape in the sky. And it does this on a time scale of about 25,770 years. Now, this is something you do have to take into effect over longer timescales. First of all, it means that currently, if you extend our axis out into the celestial sphere, we have Polaris, the polar, is the pole star. It's the star that's closest to the pole. Now, this is the circle that is traced by the extension of our, that north celestial pole against the stars over a period of time. So 3,000 years ago, the star Thuban in Draconis, Draco here, was our pole star. In about 14,000 years, the bright star Vega will be our pole star. So the pole star is changing. And that also means that because this is moving around in the sky, the celestial equator is moving around in the sky compared to the rest of the solar system plane. And so the vernal equinox is moving up and down the sky. And so our coordinate system shifts all the time. And this point, at the minute, it's over here. But back in Babylonian times, it was more around Aries here, first point of Aries. And so all our coordinate system is shifting. So if you ever specify coordinates for an astronomical object, you need to say which epoch, so where's your start point in the sky. And this is relevant, of course, if you want to compare ancient observations with current ones. You need to account for this long-term shifting of the Earth's behaviour. Okay, so the pole is sweeping out a circle in the sky. That's not all. I said that the shift of the pole doesn't change. Well, actually, that's not true. You have something called nutation. Now, all of these are ramifications of gravitational pulls on that bulge, again, the sun and the moon and the way they shift. And these are much more subtle effects. Now, currently, the Earth's tilt is about 23.4 degrees, about halfway on its cycle. And this is nutation. It's a nodding action, ever so slight, but as well as going round, the Earth tilt nods up and down. And there are various cycles. The dominant one's about 18.6 years. But you have this sort of nodding effect. And there isn't just... And, there are other subtle effects. And not just that, where the North Pole emerges from the Earth also changes. Here's a map of how the North Pole wanders across the surface of the Earth. And again, this is just a similar nutation. And this is the average position of the North Pole. It's not far. You're talking about 9 metres about every sort of 14 months or so, or maybe it's a bit longer, about every 435 days. And then there's other cycles that are about 7 years. But altogether, you've got a lot of things that are happening within the mechanics of just the rotation and the axial tilt of the Earth. But that's not all. The orbit of the Earth precesses around the Sun. So it moves, again, on very long timescales. Not just that, the shape of the orbit changes on timescales of 100, years, and there's another cycle of about 400,000 years. Again, minute variations, but it gets slightly more circular and then slightly more squashed and slightly more circular. It doesn't actually change the length of our year because that depends on the sort of length of the long axis of our elliptical shape. But nonetheless, it squeezes and it changes. And then there's also an effect of the tilt relative to the solar system of our orbit. And all of these can have cumulative effects. You may have heard of Milankovitch cycles. This is the idea that every so often these cycles of tilt and rotation and precession and what's happening within the orbit might combine to affect long-term the solar radiation we receive and the intensity. Obviously, it's different as to where you are on the near point to the far point from the sun, but if those near and far points change, and they happen also depending on the change in the axis, the idea is that every so often all these cycles will come together and maybe promote long periods of ice ages here on Earth. And there is some evidence from core sediments of lakes that perhaps this may have happened. And so you have a whole lot of effects. So that's what we understand now. But if we go back to the 17th century, you still have a problem that the Earth has not been observed to move. We know it rotates, this is what we know now, but stellar parallax still had not been observed. And this was seen as the key indication that the Earth rotates around the sun. Now, one of the first people to use a telescope to try and measure this was, in fact, a Gresham professor. Gresham Professor of Geometry, Robert Hooke. And in 1669, he decided to test this. And he would look for this annual displacement of a star against the background stars. And to do this, he built what's known as a zenith telescope. And he built this into his apartments at Gresham College, as one does. And it's a very long telescope pointing straight up. And the observer lies on the ground floor in this chair. And he had to cut a hole in the first floor and then in the roof for the telescope to look straight up. So you lie underneath, and what you do is you observe the position of a star, and the star he chose was Gamma Draconis, which is, I believe, that one. And the reason he chose that, because it's a bright star, and the idea is that bright stars might be nearer and therefore show more of that displacement. It was bright enough to be seen in the daytime, and not just that, that it was quite close. It passed overhead from the vantage point of London, which meant you didn't get refraction or atmospheric effects which would displace appeared to displace the position of the star. And so he made his observations, and the idea is you look when Gamma Draconis moves exactly overhead, you measure its angular displacement from the pole star, and if you observe parallax, then that should change over a year. Now, Hooke published 4 observations in 1674 and claimed to have discovered this parallax. This was not widely believed. Something didn't quite fit, and so astronomers kept on looking for this parallax. Hooke's observations weren't good enough, including James Bradley, who turned out to be third Astronomer Royal. He had a bigger, better zenith telescope. He again tried to observe the stellar parallax of Gamma Draconis, again drew a blank. But what he discovered instead, not parallax, but he still discovered proof, serendipitously, he wasn't looking for this, that the Earth moves round the sun. Because he saw a displacement in the position of Gamma Draconis relative to the pole star, but it was 3 months out of phase. It didn't behave as you'd expect from the stellar parallax. Instead, he discovered something called aberration, which is completely due to the Earth's motion. Now, the standard analogy here is if it's raining and you're standing still, the raindrops appear to come from straight above. But if you have motion through the raindrops, the raindrops appear to come from an angle in front of you. Now, it's not very different if you're on a moving Earth. If your telescope was stationary, you just stay put and you let the light fall down. If the Earth is moving towards the stars, you have to change the angle of the telescope slightly. And it's to do with the fact that light takes a finite time to travel. And even just while it travels down that tiny distance of a telescope, the Earth has moved forward just a little bit. And therefore, you have to change the tilt of the telescope. So this is what Bradley discovered. Now, he didn't realise this at first. He'd seen this annual pattern in the motion of the stars. He couldn't work out what it was. The story is that his breakthrough moment was actually on a boat on the Thames, where he noticed that when the boat changed course, a little flag flying in the mast showing the wind direction also changed. And he realised that it wasn't that the wind was always changing direction, but because the boat moved under the flag, it created a change in the direction of the flag. And if you're doing observations from not a moving boat, but a moving Earth, aberration also comes into account. And it has an effect that it displaces the star in the motion of the Earth's travel, which makes it 3 months out of phase from what you'd expect from the parallax. So here's your parallax argument, that from different places in the orbit, the maximum displacement in January and July, in April it's around that side. You have a definite pattern. But with aberration, you always have forward motion, and what you observe is then 3 months out of sync from the parallax. And this aberration dominates the motions of the stars relative to another. And he did lots more experiments. He built another bigger, better zenith telescope with a wider field of view. And what he noticed is that all the stars in the same part of the sky show the same annual pattern of aberration. So the key thing here is aberration depends on where the star is in the sky. It also depends on the rate of Earth's motion. It doesn't depend on how far away the star is. And so he was able to measure the motion of the Earth at about 10,000th the speed of light, which we now know means that the Earth is moving to about 30 kilometers per second around the Sun. In fact, parallax was not observed till a lot later, till 1838, and it was first observed by Bessel. And he observed two stars that were close together in the sky. Now, Gamma Draconis actually turns out to be too far away. You have to observe something quite near, and Bessel was observing 61 Cygni, which at 10 light years distance shows a much bigger parallax, because remember, parallax is stronger the closer you are to Earth. So you have two stars at different distances, same part of the sky, they show the same aberration. That allows you to take out the aberration, and then any residual motion is due to the parallax. And it was only at that point that you have the proof of the parallax of the star's motions, and this is crucial. Not just for proving the Earth moves around the Sun, but of course that allows us to get the distance to the stars. As soon as you get the distance to the stars, you know how you can compare their relative properties, such as their brightnesses. And from that, you start to compare compare stars and their physical properties, and therefore how stars work. So that was our crucial point. And a little later on in the 19th century, of course, you begin using astrophotography, which revolutionises the mapping of the sky. And by the start of the 20th century, there were quite precise atlases and precise positions of stars mapped throughout the sky. Of course, there were other problems about frames of reference. You have the positions of the stars mapped, but there's still this idea of what is the Earth moving through, what's it moving relative to. We know how it's moving relative to the solar system. But there was another problem around at the time, the latter part of the 19th century, which was the problem of light. Newton had proposed light travels as a particle. The experiments of Thomas Young had demonstrated that it behaved as a wave. And then Maxwell derived his equations for electromagnetic behaviour, and he showed there's a theoretical speed at which light travels, and that light travels as a wave through the same medium that's responsible for these sort of electromagnetic variations. And the big debate at the time was, okay, well, if light's a wave, what is that wave travelling through? We know sound waves travel through air, we know water waves travel through water, and what can a light wave travel through? And it was proposed at the time there was this ether that filled space, and didn't just fill space between the planets and the sun, but must go all the way out to the stars to carry the light from the stars back down to the Earth. And so could we detect the Earth's motion through this space-pervading ether? And one of the ways of detecting it was to use what Maxwell said, that there's a theoretical speed of light. Well, as the Earth moves in different directions through the ether, can this constant motion, the wind created by the Earth moving through the ether, can we measure the speed of light from our frame of reference, which is the Earth? and see how it varies from different parts of the orbit and also in different directions. Therefore, can we get a frame of reference and measure how the Earth moves relative to the ether? Now, it ends up being quite a complicated story, but the first experiment was done in 1881, and then a refined experiment in 1887 by Mitchelson and Morley, and where they split light in two perpendicular directions, one which would be affected more by the Earth's motion relative to the ether than the other. And they were looking for discrepancies in how the light moved in these two directions. And what they found was that there was no motion with respect to the ether. The motion of the Earth with respect to the ether was 0 kilometers per second. Therefore, even though we knew the Earth was rotating and moving around the sun, it wasn't moving relative to the ether. So the conclusion is there is no ether. Now, this experiment, of course, has been repeated many times with increased sensitivity. But this was the breakthrough that showed, in terms of frames of reference, there is no ether, that the speed of light does not change according to the motion of the observer. And it starts setting the scene, obviously, for Einstein's ideas about frames of reference and relativity. So let's move to the current day. We know the Earth is turning. Depending on where you are on the Earth, of course, you can, if you're on the equator, you're moving at speeds about 1,600 kilometers an hour. The Earth is then moving around the sun at rates of about 107 million kilometers an hour. And then the sun has its own journey through our galaxy. Now, again, you need to define what it's moving relative to. And we create what's called a local standard of rest. You sum up all the motions of all the stars near to us in the galaxy. And what you find is that local standard of rest, that solar neighborhood, is moving once around the galaxy at around every 225 million years. We're moving at a rate of 220 kilometers per second around the galaxy. So, in respect to that local neighborhood, the sun is also moving relative to those stars slightly faster at 19 kilometers per second. It's moving slightly more towards the center of the galaxy and slightly north out of the galactic plane. And so the sun has got its own journey through space. And not just that, the galaxy also is being pulled around by the gravity of nearby galaxies and superclusters of galaxies. So the galaxy itself has a journey. And trying to determine that journey gets more and more complicated, again, for frames of reference. Now, we can use the microwave background from, I refer you to my last lecture on the echoes of the Big Bang. For those who weren't here, the brief story is there's a uniform light that fills the sky at microwaves. It's not quite uniform. One fundamental thing is that we see in one part of the sky is red-shifted, one part of the sky is blue-shifted, due to the Earth's motion. And this motion is about 370 kilometers per second. And that's due to the motion of the galaxy being pulled around by the gravitational forces. But of course, all of this we want to refine. Again, it's extending our frames of reference. Now, we use parallax all the time to continuously map the sky. In the 1990s, there was a satellite called Hipparcos, which measured precise positions of 120,000 stars. And that mapped out our nearby galaxy and how all the stars were moving relative to us and how we were moving relative to them. The next generation satellite mapping is Gaia, launched in December last year. It's going to go to 100 times better precision than Hipparcos. It's going to go 100 times further. It's going to measure stars out to 30,000 light years away from us, measure their exact distances, their exact motions relative to us, and get this full 3D mapping so we can see how the sun moves relative to the stars. But not just that. The final step is to get a better reference system for how the galaxy moves. And again, this is where Gaia will help. Because if all the stars are moving relative to the galaxy and the galaxy is moving through space, you need an absolute fundamental reference frame. Grid points scattered throughout the sky in every direction, ones that don't move due to, obviously you take the aberration out, but they're so far away that you don't get the annual parallax. And Gaia will also measure the positions of tens of thousands of quasars. So far away, their positions will be fundamentally fixed. And hopefully within the next 5 to 10 years, we're going to have an intergalactic reference frame of all these distant quasars. And by then, we can truly see how not only the Earth moves through space, but how our sun moves through space and the galaxy it's embedded in. And that's going to be a completely different story. Okay, that's the end of today's talk. I'm just going to end up a flyer for next year's talks, and I look forward to seeing some of you next year. Thank you.